Hello, my dear students. Welcome to IKSR chemistry classes. In this video, we are going to discuss F-19 NMR spectroscopy, which belongs to inorganic spectroscopy. It is a very important topic for MSc final year inorganic chemistry students. Questions related to this topic are asked frequently in general examinations as well as in competitive examinations also. General information regarding F-19 NMR spectroscopy. Fluorine with mass number 19 and atomic number 9, that is F-19, is the naturally occurring isotope of fluorine. Its abundance is 100%. It means a given sample of natural fluorine consists of 100% F-19 and no other isotope. The nuclear spin, that is I, of F-19 is 1 by 2. The I value of H is also 1 by 2. The GN value of F-19 nucleus is 5.257. Please note that the GN value, that is the nuclear splitting factor value of hydrogen atom, is 5.585. 5.585 is the GN value for proton, while the GN value for F-19 nucleus is 5.257. These two values are comparable. A spectroscopic specification. The F-19 NMR spectra are scanned at 1.4 Tesla applied magnetic field, and the appropriate source of radio frequency equal to 5.646 megahertz. It means during scanning F-19 NMR spectra, the applied magnetic field is kept about 1.4 Tesla and the radio frequency of 5.646 megahertz is used. Please note that during scanning H1, that is PMR spectra, the applied magnetic field is kept about 1.5 Tesla and the radio frequency used is 64 megahertz. And these values are comparable and therefore no major modification is required in NMR instrument on shifting from H1 to F-19 work. The NMR instrument used for scanning PMR, proton magnetic resonance spectrum, can be used to scan F-19 NMR spectra with only slight modification. Chemical shift and reference. The most commonly used reference compound in F-19 NMR spectroscopy is CFCl3, trichlorofluoromethane. It is the reference in most of the F-19 NMR spectroscopic studies. The chemical shift of this compound has been taken to be 0. Please note that during scanning proton magnetic resonance spectra, tetramethylsilane is used as reference whose chemical shift is also regarded equal to 0. But in F-19 NMR spectroscopy, CFCl3 is used as reference and its chemical shift is equal to 0. The other reference compound in F-19 NMR spectroscopy is trifluoroacetic acid. Its chemical shift relative to CFCl3 is minus 76 ppm. These two compounds are used as reference in NMR F-19 NMR spectroscopy. Chemical shift variation in F-19 NMR spectroscopy. In H1 NMR spectroscopy, that is in PMR spectroscopy, the chemical shift generally varies from 0 to 10 ppm. But in the F-19 NMR spectroscopy, the chemical shift varies in a more wider range from plus 550 to minus 250 ppm. This is much more wider range than 0 to 10 ppm, which is chemical shift in the case of PMR spectroscopy. The chemical shift of CFCl3 is equal to 0, and the chemical shifts of some other organic compounds containing fluorine are given here. The chemical shift of CH3F is about minus 270 ppm. The most commonly chemical shifts in F-19 NMR spectra of organic compounds are in the range 0 to minus 270 ppm. The chemical shift in F-19 NMR spectra of most of the organic compounds generally lie in the range 0 to minus 270 ppm. But the chemical shift in F-19 NMR spectra of inorganic compounds varies in a more wider range, minus 450 to plus 450 ppm. This is the chemical shift range for inorganic compounds in F-19 NMR spectra. But in the case of organic compounds, this chemical shift is generally in the range 0 to minus 270 ppm. Coupling constant. The interaction between two adjacent nuclei having non-zero nuclear spin results in a splitting. That is a splitting up of NMR signal, and the spacing between two consecutive lines due to two consecutive lines in a NMR signal is called coupling constant. It is denoted by J. The coupling constants between F-19 nuclei having I equals to half are in a more wider range than the coupling constants for protons, as evident from the following table. The interaction between two F-19 nuclei takes place to a greater extent than the interaction between two protons, and it results in the fact that the coupling constants between two F-19 nuclei are in a more wider range than the coupling constants for protons, and this fact is evident from the table given on the next slide. Relationship between two F nuclei and coupling constant, that is JFF. This is coupling constant between two F nuclei in Hertz. If two fluorine atoms are present on the same carbon atom, it is called geminal coupling, and its value is generally in the range 43 to 370 Hertz. And if the distance between two fluorine atoms is increased and these are present on adjacent carbon atoms, it is called vicinal coupling, and its value is lower, 0 to 39 Hertz. And if two fluorine atoms are present on the same side of carbon-carbon double bond, the coupling constant is 0 to 58 ppm. While if two fluorine atoms are present on opposite sides of carbon-carbon double bond, it is called transcoupling, and the coupling constant lies in the range 106 to 148 Hertz. And if two fluorine nuclei are present at a distance 5 or more bonds, long range coupling value is 0 to 18 Hertz. This value is the minimum. It is obvious that as the distance between two F nuclei increases, the interaction between these nuclei takes place to a smaller extent, and as a result, the FF coupling constant goes on decreasing. If two fluorine atoms are present at a distance more than 5 covalent bonds, here the distance is 1, 2, 3, 4, 5, and this value is 0 to 18 Hertz. And on further increasing the distance between two F nuclei, the coupling constant goes on decreasing. Coupling between H1 with I equals to half and F-19 with I equals to half nuclei. Coupling between proton and F-19 nuclei may also take place, and these are the coupling constant JHF, that is coupling constant between H1 and F-19 nuclei. If H and F nuclei are present on the same carbon atom, the coupling constant is 42 to 80 Hertz. And if two hydrogen and fluorine nuclei are present on adjacent carbon atoms, the coupling constant is 1.2 to 29 Hertz. If H and fluorine nuclei are present on the same side of carbon-carbon double bond, the coupling constant is 0 to 22 Hertz. If H and fluorine nuclei are present on the opposite sides of carbon-carbon double bond, the coupling constant is 11 to 52 Hertz. And in the case of fluorobenzene, the coupling constant decreases with increase in distance. If fluorine and H atoms are present at ortho positions, the coupling constant is 7.4 to 11.8 Hertz. If hydrogen and fluorine nuclei are present at meta positions, the coupling constant is 4.3 to 8 Hertz. And if fluorine and hydrogen nuclei are present at para positions, the coupling constant is very small, 0.2 to 2.7. Here also it is evident that as the distance between hydrogen and F-19 nuclei increases, the coupling constant decreases. F-19 NMR spectrum of ClF3 at minus 60 degrees centigrade. The F-19 NMR spectrum of ClF3 at or below minus 60 degrees centigrade consists of two signals in the ratio 2:1. This is F-19 NMR spectrum of ClF3. It consists of two signals. One signal is here and it is another signal, and the area below these signals are in the ratio 2:1. a doublet. This is doublet. The NMR signal splits up into two peaks, and this doublet is obtained at -4 ppm and a triplet at +116 ppm. This NMR signal splits up into three peaks, and this triplet signal is obtained at +116 ppm, while this doublet signal is obtained at -4 ppm. It rules out the possibility of triangular planar and trigonal pyramidal geometry for this molecule. Since two NMR signals are obtained in the F-19 NMR spectrum of ClF3 at or below -60 degrees centigrade, the possibility of triangular planar and trigonal pyramidal geometries are ruled out, because in triangular planar geometry, three F atoms are present in the same environment and a single signal is expected in F-19 NMR spectrum. In trigonal pyramidal geometry also, three F atoms are present in the same chemical environment and only one NMR signal is expected in F-19 NMR spectrum, and hence ClF3 molecule cannot have triangular planar or trigonal pyramidal geometry, and therefore T shape has been suggested for ClF3 molecule. ClF3 molecule has T shape. This is T-like shape. In this geometry, two axial fluorine atoms are present in one chemical environment, while the equatorial fluorine atom is present in another chemical environment. The NMR signal due to axial fluorine atoms splits up into two peaks due to interaction with this F-19 nucleus present on the equatorial position, while the NMR signal due to this equatorial fluorine atom splits up into three peaks due to interaction with these two fluorine nuclei present on axial position. F-19 NMR spectrum of ClF3 above -60 degrees centigrade is given here. It at 60 degrees centigrade, the NMR spectrum of ClF3 is given here. It consists of the F-19 NMR spectrum of ClF3 above -60 degrees centigrade consists of only one signal at 56 ppm. This value, this signal is obtained at +56 ppm, which is the mean of -4 ppm and +106 ppm. It has been explained on the basis of Berry pseudo rotation. At higher temperature, the axial and equatorial fluorine atoms exchange their positions rapidly by a phenomenon known as Berry pseudo rotation. This is ClF3 molecule having T shape. This axial fluorine atom and this equatorial fluorine atom exchange their positions rapidly due to a phenomenon known as Berry pseudo rotation, and due to this, the equatorial and axial fluorine atoms of ClF3 molecule become equivalent and they give rise to a single signal in F-19 NMR spectrum. The F-19 NMR spectrum of ClF3 molecule at above -60 degrees centigrade, such as +60 degrees centigrade, consists of a single signal because the equatorial and axial fluorine atoms exchange their positions rapidly due to very pseudo rotation and they become equivalent. But below minus 60 degrees centigrade, very pseudo rotation is arrested, is seized, and the equatorial and axial fluorine atoms become non-equivalent and they give rise to two signals in F-19 NMR spectrum. Below minus 60 degrees centigrade, the F-19 NMR spectrum of ClF3 consists of two signals, while above this temperature, the F-19 NMR spectrum of ClF3 consists of only one signal. F-19 NMR spectrum of SF4. F-19 NMR spectrum of SF4 at or below minus 100 degrees centigrade consists of two signals in the ratio 1:1. This is F-19 NMR spectrum of ClF4 molecule at minus 100 degrees centigrade. It consists of two signals and the area below these signals are in the ratio 1:1. Please note that both the signals are triplet. A triplet signal is obtained at minus 90 ppm, while the other triplet signal is obtained at minus 35 ppm. And this is the coupling constant between two F nuclei and it is equal to 79.9 megahertz. Please note that the distance between two consecutive lines in a multiplate signal of NMR spectrum is called coupling constant. It rules out the possibility of square planar or tetrahedral geometry for this molecule. Since two NMR signals are obtained in the F-19 NMR spectrum of SF4 below minus 100 degrees centigrade, it's all the fluorine atoms are not present in the same chemical environment and therefore the square planar geometry or the tetrahedral geometry for this molecule is ruled out because in both these geometries all the four fluorine atoms are present in the same chemical environment and accordingly seesaw shape has been suggested for SF4 molecule. This is seesaw shape for SF4 molecule. These two fluorine atoms are present on the axial positions while these two fluorine atoms are present on equatorial positions. The axial and equatorial fluorine atoms are present in different chemical environments. Two axial fluorine atoms are present in one chemical environment while two equatorial fluorine atoms are present in another chemical environment and therefore the F-19 NMR spectrum of SF4 below minus 100 degrees centigrade consists of two signals in the ratio 1:1. One signal is obtained at minus 90 ppm while another signal is obtained at minus 35 ppm. And it rules out the possibility of square planar and tetrahedral geometries for SF4 molecule and therefore seesaw geometry has been proposed for this molecule. But the F-19 NMR spectrum of SF4 above minus 100 degrees centigrade consists of only one signal at minus 63.5 ppm, which is the mean of minus 35 and minus 90 ppm. Only a single signal is obtained in the F-19 NMR spectrum of SF4 at 23 degrees centigrade and this signal is obtained at minus 63.5 ppm. It has been explained on the basis of very pseudo rotation. At higher temperature, the axial and equatorial fluorine atoms exchange their positions rapidly as a result of very pseudo rotation. This is SF4 molecule having seesaw shape. This equatorial fluorine atom goes to axial position, while this axial fluorine atom comes to equatorial position, and this process takes place very rapidly. As a result, the equatorial and axial fluorine atoms become equivalent, and a single signal is obtained in F-19 NMR spectrum of SF4 above minus 100 degrees centigrade. As a result, the equatorial and axial fluorine atoms become equivalent, and they give rise to a single signal in F-19 NMR spectrum. But below minus 100 degrees centigrade, very pseudo rotation is arrested, and the equatorial and axial fluorine atoms become non-equivalent, and they give rise to two signals in the F-19 NMR spectrum. And let us now see SOF4. The F-19 NMR spectrum of SOF4 has only one signal. It means it's all the four fluorine atoms are present in the same chemical environment. The F-19 NMR spectrum of SOF4 consists of only one signal. It means all the four fluorine atoms of SOF4 molecule are present in the same chemical environment, and they are equivalent. On this basis, the following square pyramidal structure for SOF4 molecule has been suggested. This is the proposed shape for SOF4 molecule on the basis of F-19 NMR spectrum, which consists of only one signal. It means it's all the four fluorine atoms are present in the same chemical environment. Thank you for watching the video with concentration and patience. Please like and share it. And if you have not subscribed my channel yet, please subscribe it so that you may get information regarding my new videos in time. Thank you again.